Hello, in this video I'm going to give an introduction to graphing. Specifically, how graphing is used in physics, but the same techniques can also be used in other science classes as well as most math classes. We can use graphs to discover the relationship between two different variables. For example, what you make a bridge out of and the strength of that bridge. What might be new to some of you is that then we take it one step further. It isn't enough to know that steel makes a stronger bridge than stone, but we want to discuss and find the mathematical relationship between those, and then to build a mathematical model that will allow us to make quantitative predictions. Predictions that have numbers. So then we can know how strong a bridge is and therefore put the weight limit sign off without having to drive heavier and heavier trucks over the bridge until it collapses and then rebuild the bridge. As an example, let's take something from thermodynamics that you may have done in chemistry class. Let's start with a 1 liter pressurized cylinder and put that on top of a ring stand, and then put a Bunsen burner underneath. When you turn the flame on, that's going to increase the temperature of the gas inside. So temperature is going to be our independent variable, the one that we have some modicum of control over. And pressure is going to be our dependent variable, the thing that we are studying how temperature affects. And throughout this, we are going to hold several other variables constant. For instance, the volume of the container is not going to change, and because it's a sealed container, the amount of gas inside is similarly going to remain constant. So let's say I run this hypothetical experiment. I'm going to make a data table with temperature, measured in degrees Celsius, and pressure, measured in atmospheres. And I'm going to put my independent variable on the left and my dependent variable on the right. And then I'm going to start filling in the data. Unsurprisingly, at room temperature, we have 1 atmosphere. But as things start to heat up, it's also staying at 1 atmosphere. That's just because my pressure sensor is only limited to the 10th of atmospheres. So at 40 degrees C, still only at 1 atmosphere. But when we start climbing up to 59, it's now at 1.1. And you notice how my independent variable, the temperature, isn't round numbers. And it doesn't really have to be. All that matters is that at 151 degrees C, the pressure is 1.4 atmospheres. Just having a table, though, doesn't really give me that much information. In order to really understand the relationship between temperature and pressure, I need to make a graph. And when making that graph, I'm going to make sure that it has all the important parts, like a title, in this case, how temperature affects pressure. I could be more creative, but I'm not. And I also need to make sure I label my axes. Also remembering that each axis not only needs a label, but also a unit for that label as well. Temperature, because it is my independent variable, is going to go along the x-axis, and pressure, the dependent variable, is going to go along the y-axis. As I put the numbers in for my graph, note that I am putting my highest value all the way to the right and 0 all the way to the left. This will ensure that we can get a good visual range on the data and understand what's really going on. So I'm not putting any of the jump symbols in. I am making sure that there is an equal distance in value between each point on the graph. From here, it just becomes a matter of putting the data points in the correct position. So 25 degrees and 1 atmosphere, 30 degrees, also 1 atmosphere. Same way with 40. Now at 59, we're starting to jump up to 1.1, so that's going to be about here. And then 92 degrees, that's going to be 1.2, so right about that looks good. And then 151 degrees, so that's a big jump along the x-axis, but we're now at 1.4, and then 200 is going to be about 1.6. Now, at this point, what I am not going to do is play connect the dots. It has been a very long time since I have been in kindergarten, so instead, what I'm going to do is find the line of best fit. So I'm going to take my protractor, not to be confused with an anti-tractor, and put that along the average of the points. So you might notice that there are some points that are going to be above and some points that are going to be below the line, but this does a good job right about here of fitting the data overall. So I'm making this a dashed line so you can see where the original data points are, and you can see that, yeah, it's a decent fit for the data that we have. Also, we can look at this and see that it is a nice straight line. So this is what we call a linear relationship. And we love linear relationships because they follow the equation that we learned in algebra class, y equals mx plus b. M, of course, is the slope of the line. And slope is calculated by taking the rise over the run. And the rise is equal to the change in y, or delta y, and run is delta x, or the change in x. And that's essentially the final of y minus the initial of y over the final of x minus the initial of x. So, in order to calculate for this, what we're going to do is look and find 2 points that are far apart that are actually on our best fit line. So the first one looks like 200 degrees and 1.6 atmospheres. And then looking all the way to the left, that one looks like it's almost exactly 0.9, and that would correspond with 0 degrees C. So doing some quick math, that's going to equal 0.7 divided by 200, and then that's going to give us an answer of 0.0035. And of course, B represents the y-intercept, which we can read off of the graph, which in this case equals 0.9. We have now done all the calculations we need in order to fill out our y equals mx plus b. So y equals m, the slope, and that was 0.0035 times x, plus b, our y-intercept, which was 0.9. But we're going to take that one step further, because here our line actually represents something. We have pressure for y, temperature for x, and we can put that into our equation so the equation tells us more. Y is pressure, and that equals 0.0035, and the units of that would be units of rise, which is atmospheres, over units of run, which is degrees C, times our x value, which is temperature, plus the y-intercept, 0.9, and the units of that is in atmospheres. So now we have our complete equation. So a couple things to note. We've got rid of the x and the y, and that all of our numbers have the appropriate units attached to them. But p and t don't have units, since that would be redundant. So here we have it, our complete equation. Pressure equals 0.035 atmospheres per degree Celsius times the temperature plus 0.9 atmospheres. This equation gives us a wonderful relationship between pressure and temperature in degrees C. The only thing that would be even better is if instead we had a direct relationship, one where we didn't have a y-intercept, or one that had a y-intercept equal to 0. And the way that we could do this is invent a unit of temperature that had 0 where volume equaled 0, and that is what we call the Kelvin. Since the increments of the two temperature scales, Celsius and Kelvin, are the same, and the only difference is the starting point, we can take this one step further and say that pressure is directly proportional to temperature, measured in Kelvin, or that pressure equals the temperature in Kelvin times some constant K of proportionality. And we can take this one step more and say that pressure equals that constant of proportionality of 0.0035 atmospheres per Kelvin times the temperature measured in Kelvin. At this point, we can say that we have a good start towards experimentally creating the ideal gas law, or PV equals nRT.